So hopefully everyone's coming up with the same thing. I'm going to first protonate the carbonyl group with the carboxylic acid to make it more electrophilic using our acid. Now our nucleophile is internal. So we're going to have form this intramolecular reaction of forming a ring. So the hydroxyl group will attack the carbonyl carbon, including the oxygen. It's 1, 2, 3, 4, 5, 6. And so we're going to form a 6-membered ring. Now we have a couple of proton transfer steps. We're going to take a proton off, or what was the alcohol, removing that positive formal charge and placing it on hydronium. Now I'm going to turn one of these two hydroxyl groups into a good leaving group by protonating it, and that's where I'm at here. And now let's kick out our good leaving group. This is where we lost water, just like before. And now all we have to do is to deprotonate here. To generate our final product, our cyclic ester or lactone, as it's known. So same idea with the mechanism, but intramolecular. One other thing I meant to mention in the last reaction, but we can use this one, shows the same thing, is that to keep track of everything here, and is this, let's put it down here. Let's make it blue. And this is the minus water. This was the leaving group. And the reason I'm bringing this up is this reaction works by having a carboxylic acid, an alcohol, and the acid here, it's catalytic. This is what I didn't mention before. It only takes a very small amount of acid to get the reaction to go. And so it's a catalyst, which means it's not consumed in the overall reaction, right, from the definition. Let's see if that actually makes sense. And so we started off with a 1 mole here, let's say, of the hydronium, and it donates the proton, so it becomes water. And then as we go to the next step here on the right, it's going to pick up a proton. So we've regenerated our hydronium, so we're back to where we started. And then here, as we've released the water here in the end, we're going to pick up a proton again and end up with hydronium. Yeah, so let me write that over here on the right. So it doesn't take much acid for this reaction to happen. Okay, any questions about the Fischer esterification? Hopefully I can see the connections to some of our earlier carbonyl chemistry as well, where we protonate this carbonyl group now to make it a much more electrophilic center. As opposed to an aldehyde or a ketone, now it's a carboxylic acid. In the last 3 minutes here, let's look at a couple of reactions with the esters. And or some common ones is what's known as hydrolysis here. So we can have our ester react with water in the presence of acid or base under acidic or basic conditions. And we're going to end up with a carboxylic acid and then an alcohol in the end. So I mentioned this can be done in the presence of acid or base. And I have the acid one first, the base one should be down here. Yep. And so let's take a look here at the acid catalyzed reaction. And this we'll use it's actually the reverse of the Fischer esterification. So we're going to be doing essentially the same thing, but let's just do it in reverse and see if this works out. So let's consider, why don't we just use this methyl ester here. Now we have water as our weak nucleophile. Just like before though, with our carboxylic acid, this carbon, it was electrophilic, but not nearly as reactive as that acyl chloride because the oxygen is donating some electron density back into resonance. So let's make this much more reactive by having our little bit of acid, so H3O plus around. So we're going to speed up or catalyze the reaction. We're going to generate the protonated species. So just like before, also under acidic conditions, positive formal charges here. So now this carbonyl carbon is much more electrophilic, so we can have our weak nucleophile water attack. These electrons up onto this oxygen. These steps are also all in equilibrium. OH, OCH3, and then this with the positive formal charge in this oxygen. Now let's take that proton off, regenerate our acid. OH, OCH3, OH here, plus H3O plus. Now this is where we have a decision to make. We could go ahead and reprotonate this hydroxyl group, which will just go back to this step here. We'll go in reverse, and that's actually under equilibrium conditions this will happen. We protonate this top hydroxyl group, and we'll end up with the same thing because these two hydroxyl groups are the same. So this will happen, proton will come on, proton will come off, these two species will be in equilibrium, but then sometimes this hydroxyl group, this oxygen will get protonated. So let's see what that does. So now we have another equilibrium going down below where we've protonated this one on the right. Now we made a good leading group there. So let's go ahead and kick that group out. So here we lost methanol. We still have a positive formal charge. Now all we have to do is to deprotonate to reform our carbonyl group. And we regenerated our acid. And then here we've lost plus methanol down here. So this is the reverse of that Fischer esterification. In this case, we started out with an ester, and we end up with a carboxylic acid and an alcohol. All of these steps are in equilibrium. One thing I should note is if we draw this actually in the opposite direction, which you'll end up noticing is that a lot of times these arrows will be in the opposite direction. So if we protonate it in one direction, we'll deprotonate in the other direction. And what's actually happening here, I'm running over, is that like in this step up here in the upper right of the mechanism, all these steps are in equilibrium. So the proton occasionally gets on one of these oxygens. You may end up kicking that water out and you'll be back over at this material here. So all of these steps are going back and forth in equilibrium. Occasionally this group here is going to get protonated. Which then if it gets protonated, maybe it gets kicked out. If it doesn't get kicked out, it's deprotonated, you're back at this step here. So all of these steps are in equilibrium. We can drive the reaction forward by changing the concentrations of the reagents or by removing methanol, for example. So these are very important reactions, especially with esters. We can make them using the Fischer esterification. We can react them to form carboxylic acids, going backwards to the reverse under acidic conditions. Next time where we'll start is under basic conditions to hydrolyze this. So simpler reaction mechanism. And then we'll finish our discussion of esters and continue with amides as one of the last carboxylic acid derivatives that we want to discuss. So sorry for running over a couple of minutes here, but hopefully we see the common features of these reactions of these carboxylic acid derivatives. Otherwise, I will post some more practice materials here later today and hang around for questions. Otherwise, I'll see everyone tomorrow.